All right, welcome to section 3.4. We'll look at a little algebra review because there's going to be a lot of rationalizing and complex rationalizing fractions and complex fractions that we have to work with. So here we're going to turn these into binomials. We're going to multiply the top and the bottom by the complex of the bottom. So that's 1 plus the square root of 3, which these two are technically the same, so I'll treat this as 1 plus the square root of 3. When I FOIL that out, I'll get 1 plus 2 square root of 3 plus 3. And on the bottom, you'll get 1 minus 3. Combine like terms, we're going to get 4 plus 2 times the square root of 3 over negative 2. So we want to cancel that negative 2 on the bottom. So we're going to factor out a negative 2 from the top. We'll cancel that. So that negative 2 factored out leaves us negative 2 minus 1 times the square root of 3. The negative 2's cancel, leaving us negative 2 minus the square root of 3. You want to check with your calculator. Square root of 3 plus 1, 1 minus the square root of 3. There's your decimal representation. There's your negative 2 minus square root of 3. That all checks out, and I would recommend doing that so we don't make any sign errors or radical mistakes or anything like that. All right, our complex fractions, I'm going to treat those like a binomial on the top. Take a look at each individual denominator. We're going to take its least common denominator. Between 5 and 3 will be 15, so we're going to multiply the top and the bottom by 15. So distribute in the 15. 15 times 1 is 15, but here into the fraction, 5 goes into 15 3 times 12 will be 36. So 15 plus 36 on the top. Excuse me. 3 goes into 15 5 times the negative 4 is negative 20. We'll combine the top and we'll get negative 51 over 20. Now, in part B, we got a little simplifying we might want to do first. For example, we got to square this fraction first before we can decide to multiply. So we can't multiply the top and the bottom by 3. In fact, I would probably multiply the 2 to the 5 and make that 10/3 and leave this as 1 minus 4/9 on the bottom. Oops. There was my fraction check for A. So after simplifying this here, now, between the 3 and the 9, the least common denominator will be 9. So that will give me 30. And I'll have 9 minus 4, which is going to be a 5. And 30 over 5 is 6. And again, calculator check. Well, part of my calculator's falling off the screen there. Does give us 6 when we enter it in. All right, so to build your double angle, we're going to go back to our sines. Cosine and tangent of our sum of two angles. But what we're going to do is we're going to make the B into an A. So we have A plus A for all of our sum identities. Well, when we simplify that, sine of A plus A, that'll be 2A. Excuse me, tangent of A plus A is 2A. Cosine of A plus A will be cosine of 2A. Now there will be 3 possibilities here that we will create. So we use our sum identity, that's sine of A cosine B, but it's going to be an A here, plus cosine A sine A. Wait a minute, these two are exactly the same. It doesn't matter which one comes first, so that's going to add together, they're like terms, to be 2 sine A cosine A. So there's your double angle identity for sine. For tangent, okay, that was tangent of A plus tangent of A over 1 minus tangent of A times tangent of A. Well, if you add the 2 on the top, they're the same. That'll be 2 tangent A, and tangent A times tangent A, that will be tangent squared A. So there's our identity for the tangent of 2A. For cosine of A plus A, remember that's cosine A cosine. 2 cosines first, then opposite sign minus 2 sines, but they're going to be the same. Cosine A cosine A, sine A sine A, well that's cosine squared A minus sine squared A, and we can't use a Pythagorean identity. It doesn't match for this one. So that's our first cosine of 2A identity. However, having 2 trig functions in your identity could be a little cumbersome, so we can simplify this 2 ways. Go to your Pythagorean identity. Cosine squared plus sine squared equals 1. I should say that properly. I should say cosine squared A plus sine squared A equals 1. We could subtract over the sine squared and leave the cosine squared by itself, so we can replace that with a 1 sine squared A. Then minus this sine squared A, that gives us 1 minus 2 sine squared A. So that's another one of our double angle identities for cosine. And we can also do the same by substituting out sine squared A as 1 minus cosine squared A. But here, got to be careful. We have to distribute that minus sign. So that will give us a minus 1 plus cosine squared A. And adding those two cosine squared A's gives us 2 cosine squared A minus 1. And there is our third identity. So this is kind of nice with these two because now this double angle identity is completely based on one trig function. So if you need sine, we'll use this one. If you need cosine, we'll use that one. Okay, example 1, finding function values of 2 theta given information about theta. So we're given that cosine theta is 2/3 and sine theta is negative. All right, so all students take calculus. We need cosine to be positive, that's 1 and 4, and we need sine to be negative, which is 3 and 4. So we're looking at a quadrant 4 angle here. Okay, so quadrant 4 angle for theta. So we need to find sine and tangent based off of our cosine of 2/3. Well, okay, that means sine will be negative and tangent will be negative when we find that. So using my Pythagorean identity, I subtracted over the cosine squared theta, seeing that I need to find sine right away. And we'll substitute 2/3 here for cosine theta and square that 2/3 to get 4/9. 1 minus 4/9 is 5/9. We'll take the square root of both sides and we will get sine theta is equal to, remember we said sine would be negative, so I put in the negative, square root of 5 over the square root of 9, which is 3. Now, tangent of theta, well, that's our sine over cosine. So I'll go negative square root of 5 over 2. Remember, we just cancel the denominators, and there's our tangent. Again, that was also negative. Excuse me. So sine of 2 theta. Grab your identity, 2 sine theta cosine theta. We'll make our substitutions. We'll plug in the negative square root of 5 over 3. We'll plug in the 2/3. We'll crunch the numbers. 2 times 2 is 4 times the negative square root of 5 is a negative 4 square root of 5 over 3 times 3 is 9. That one's done. Cosine of 2 theta. I'm going to opt for cosine squared A minus sine squared A for the following reason. Over here to the left, I found sine squared theta and cosine squared theta in my work. And that's what I need here. So cosine squared theta, that was the 4/9. The 5/9 represented my sine squared theta, so we'll just substitute those in as 4/9 minus 5/9 equals negative 1/9. Tangent squared theta, well, we could use the identity 2 tangent theta over 1 minus tangent squared theta, but this is where it gets kind of interesting because we have fractions over fractions and we got to simplify things. Again, excuse me for the chest cold I have here. 2 and the 2 on the bottom will cancel out. Here we'll square the top and the bottom, so this will be a positive 5 over 4. And then 1 minus 5/4 is a negative 1/4. The negative on the top cancels with the negative on the bottom. That makes it positive. All right, well, we don't divide by a fourth. We multiply by its reciprocal. And that's going to get us 4 times the square root of 5. Now, a more common approach, and easier, working smarter, not harder. Remember, tangent of 2 theta is the same as sine 2 theta over cotangent 2 theta. So grab the two answers you have. Negative 4 radical 5 over negative 1. We just cancel those denominators. Cancel the signs, and there's your 4 radical 5. You can get it done a lot easier that way. So work smarter, not harder. Okay, next, find the values of the 6 trig functions of theta if cosine 2 theta is 4/5 and 90 degrees is less than theta is less than 180 degrees. So theta has to be in quadrant 2. Okay, so what we need to do is we need to determine our sine of where we're going to end up at. So let's see. We're in quadrant 2 right now, so sine's positive, tangent and cosine will be negative. So I need to do some work here, so let me think. I got to grab one of these 3 double angle identities. Now the first option, cosine squared A minus sine squared A, was good for the previous problem because we technically already had found cosine squared A and sine squared A. But it's not going to be good because we would have to take 4/5 and set it equal to this equation right here, this expression. Well, cosine squared A minus sine squared A is like saying x squared minus y squared equals 4/5. You can't solve for x or y. Well, then you can't solve for cosine A or sine A. So we're going to have to go with one of these two. And it doesn't matter which one you want to use. So I'm going to opt for 2 cosine squared A minus 1. We'll throw that one out. Start with this one. So again, take 4/5, set it equal here. Or basically making that substitution. But I'm a left to right worker. I like to have my answer here to the right and my variable technically solving for cosine theta. We'll add over the 1, so 4/5 plus 1 is 9/5. Divide by 2, that's just like multiplying the 2 to the 5. We'll take the square root of both sides. That will get me 3 over the square root of 10. Now remember, we're quadrant 2, so cosine is technically a negative value there. So we can build a quadrant 2 triangle. Cosine would be -3 over 10. So -3 is the adjacent side, square root of 10 is the hypotenuse side. Your theta goes from the positive x-axis to that hypotenuse. Use the Pythagorean theorem to solve for this missing leg. So a squared plus b squared equals c squared. We make the substitutions, we square them, we solve for a. A is 1. Now, again, don't get me wrong. I want to go back here. You could have used this equation. So I'm going to quickly do this. If you want to write it down, go ahead. It doesn't matter. We could have done this. We could have subtracted over the 1. 4/5 minus 1 would be -1/5. We could divide by the -2. That gives us a positive 1/10. We could take the square root of both sides. We get 1 over the square root of 10. And again, sine is positive in quadrant 2. And you can see in the triangle, everything would have worked out the same. Opposite 1, square root of 10. You would have done the Pythagorean theorem again, but this time you would have found 3 for the answer, but then you got to make it -3. Well, now that you have your triangle, we'll start to build everything. So our sine theta, we said, was 1 over the square root of 10. Rationalize the denominator, square root of 10 over 10. Our cosine of theta was -3 over the square root of 10. Again, rationalize the denominator, -3 square root of 10 over 10. Tangent of theta would be 1 over -3, so that would be a -1/3. Your cotangent theta, well, we'll just take the reciprocal of that. That would be -3 over 1, or just -3. Secant, let's stick with the first fraction. Let's flip that one. So that's going to be the square root of 10 over -3. That's good enough. You can leave the negative on the bottom or off to the side. It's all good to me. And let's take the first fraction for sine of theta, flip that. So cosecant of theta is equal to the square root of 10 over 1. But we don't need the 1. All right, to the next example, 3. Simplify expressions using double angle identities. Okay, I see a cosine squared 7x minus sine squared 7x. Hey, that looks like this identity here before I scratched it out. So let's write that down. Realize that a is the 7x. Put that in for a. 2 times 7x is 14x. There, we simplified it. We're done. Over here, 2 times sine of 15 times cosine of 15. That's definitely my double angle identity for sine. A is 15 degrees, so again, we'll put 15 in for A. We can go ahead and simplify this now. 2 times 15 is 30 degrees, and we can take it one step further. We can take the sine of 30 degrees, which is 1/2. Oh, we got an ugly angle here for C. This definitely looks like a cosine of a double angle here. So A is playing the role of 157.5 degrees, so let's put that in both spots. Let's simplify this. Let's see, 2 times 157.5. That looks like this could be 315 degrees. Oh, let's see. That's quadrant 4 with a 45-degree reference angle. That's sine. That's going to be square root of 2 over 2, but sine's negative in quadrant 4. Oh, check that. We're looking for cosine, not sine. My apologies. Cosine of 315. That's a positive. Where did I see sine? Must have been thinking of the previous problem. My apologies. Example 4, verifying a double angle identity. This one is going to be difficult. You have to kind of look where we need to go, because you'll notice that there's a double angle in each side. So I'm going to work the left side because I've got a cotangent to work with. So I'm going to change cotangent to cosine x over sine of x, and I'm going to change sine of 2x as 2 sine x cosine x. Always better to work with the sine of 2x because there's only one possible version of it. And also, you have sines and cosines that are not raised to the second power, so it's good for canceling. So, like I said, we'll cancel those sine of x, and now we're left with cosine x times 2 times cosine x, which is 2 cosine squared x. Okay, well, wait a minute. I have cosine squared x, but I don't have a 2 multiplied to it. I have a 1. Let's see. How am I going to magically create another term? Oh, wait a minute. Cosine of 2x. If I were to put a -1 here, and I'll add 1 over to the other side, then 2 cosine squared x minus 1, that becomes cosine of 2x. That's the double angle identity right there. So in this case, we introduced a -1, but then we had to add 1, and I put the 1 plus in front because that's where I want to be first. And then the -1 after, which then turned this into a cosine of a double angle. And now we match what we have on the right-hand side. All right, so that'll take care of part 1.